Welcome to the video for C5.2.5 where we're going to look at catalysts and rate of reactions. So to start with, I want you to answer these questions. So pause the video and try and write a word and symbol equation for that reaction. Okay, so hopefully we've been able to write at least the word equation. So in the reaction between zinc and hydrochloric acid, so because the reaction is happening between them, they're the reactants that go on the left-hand side of the arrow, and the products made are zinc chloride and hydrogen. So they're the products, and they're going to go on the right-hand side of the arrow. So if I was to write this, I would write zinc plus hydrochloric acid. And then remember, it's an arrow, not an equal sign, and that's going to give my products, which we've identified as zinc chloride and hydrogen. And it gives us the symbols for these. So it gives us the symbol for zinc is Zn, and it gives us the symbol for hydrochloric acid is HCl. And then it gives us the zinc chloride is ZnCl2 and hydrogen is H2. Now that's the symbol equation, but we need to balance it. So if I look at these on the left hand side, I've got one zinc, one hydrogen and one chlorine. And on the right hand side, I've got one zinc, two hydrogens and two chlorines. So the zinc's okay, but the hydrogen and the chlorine are not. So let's do the hydrogen first. So I've got two hydrogens on the right hand side. I need two hydrogens on the left. I've only got one. So the temptation here is to say, oh, I need two hydrogens, so I'll just change that to two. But that changes the chemical formula. So we can't do that. All we can do is put a number in front of here. So if I put a big 2 in front of that, that means I've got two HCl molecules. So I've now got two hydrogens and two chlorines. So if I change this here to a 2 and that to a 2, we can now see that the hydrogens are balanced and also the chlorines. Right, so our learning objectives for today. So you need to be able to describe what a catalyst does and then explain how it works, and also explain what an enzyme is, which is a term you might have met in biology. So key facts. So we need to copy these into our notes. So the definition of a catalyst is a substance that speeds up a chemical reaction, but it's not used up in the reaction. So it's not used up, and it's not changed. Okay, so it's not changed at all. So you can have some chemicals which speed up reactions, but they get changed themselves. So if they speed up a reaction, but they're altered themselves, they're not a catalyst. It's only if they're not changed or altered or used up in the reaction. So we need to know how they work. So catalysts work by lowering the activation energy. So remember, the activation energy is when we think of our collision theory, the particles need to collide to react, but they also need to collide with enough energy, and we call that energy the activation energy. So if we lower the amount of activation energy that is needed for a successful reaction, then we're going to get more successful collisions. So normally I put the word successful or fewer in bold. I've not here. So this is a really important word, because if we don't put that in our exam answer, we don't get any marks. So that's how they work. And then underneath here, we've got some other key facts about catalysts. So catalysts are specific to a reaction. So if we've got a reaction that we can speed up with a catalyst, we'll use a specific chemical. So for example, iron is used in the Haber process to speed up the production of ammonia. There'll be other reactions. It might catalyze some other reactions, but there'll be other reactions that it doesn't. So we can't just assume that because a catalyst speeds up one reaction, it's going to speed up another reaction. Second important point is that only a small amount of catalyst is needed for large amounts of reactants. Because the catalyst is not used up, it can be used again and again and again. So, and this is important because a lot of catalysts are expensive, but that's not normally important, because we only need a small amount of it relative to the amount of reactants. Now, you might have heard of the term catalytic converter. They're used in cars, so I believe it's a legal requirement now that all cars have to have catalytic converters fitted into them, and these catalytic converters remove harmful waste gases. And in biology, you've probably met the term enzyme, and hopefully our biology teacher has talked about what enzymes do. So enzymes are biological catalysts, so they speed up chemical reactions in biological systems. So what would a reaction profile look for a reaction with a catalyst? So remember what a reaction profile is. So we have on the x-axis, we have progress of reaction. And on the y-axis, we have enthalpy, or sometimes people write it as energy. Doesn't really matter at GCSE. So for these, we have a line to represent the reactants. And then we have a line. Sorry, my pen's gone a bit dodgy. Let's just get it back. We have a line for the products. And just a bit of a revision here, this would be an exothermic reaction if I had, I'm not going to draw out the entire thing, but if I had an endothermic reaction, I'd have the reactants there and the products would be higher. So this would be endothermic. And excuse me for not labeling the axes, but it would be exactly the same. So a typical reaction profile for an exothermic, so we'd have a line to show the reactants turning into the products. And when we did these in year 10, we drew an arrow from the reactant line to the top. So I've lost my pen again. To the top of the arrow. So remember, we need to make sure when we're drawing these that the arrow A touches the line and the top. So really it's got to touch both lines. So it's got to touch the reactant line and it's got to touch this line here. And B, it needs to be single-headed. So quite often people draw these like this, and that is not allowed. Right, so this is our normal one that we've drawn before. So if we add a catalyst, what happens? So if we add a catalyst, the reactants and products stay in the same place. But this label here, so we sometimes give it the symbol capital EA. So that is the activation energy. So that's the normal reaction. If we add a catalyst, what we're doing is we're reducing the activation energy. So what we'd do is this little hill would be lower. So the difference between the reactants and products stays the same, but the activation energy, so I'll write EA and circle it. So that was without a catalyst. And the one with the circle is the activation energy. With a catalyst. So you can see that it's lower. And that means we're going to get more successful collisions. So if sometimes you're asked to draw these and label the energy change of the reaction. So this here would be the energy change. And you can see that by adding the catalyst, that has not changed. Okay, so the difference between the reactants and products has stayed the same. And again, that needs to be single-headed arrow. But if you draw a double-headed arrow, you would not get the marks. So key point that we've made before, but on the key points we said that you could use a small amount of catalyst for a lot of reactants. So if you add a lot more catalyst, it doesn't make that much difference, because a small amount of catalyst makes a big difference to the rate of reaction. When you add a lot more catalyst, it makes a little difference, but not much. So here's a typical exam question. So pause the video and have a go at this. Okay, so it's asking you which line of the table shows how the rate of reaction and the mass of the catalyst change as the reaction takes place. Okay, so hopefully you've answered C. So the rate of reaction increases, and the change in the mass of catalyst, there is no change, because when we think back to our definition, it said it wasn't used up. So our definition was that it sped up the rate of reaction, but it wasn't changed or used up itself. So because it's not been used up, the mass isn't going to change. Okay, so another exam question. So silicon dioxide is used as a catalyst. Suggest why 1 gram of silicon dioxide is more effective as a catalyst when used as nanoparticles rather than as a powder. So pause the video and have a go at answering this. Okay, so hopefully you've come up with the idea. So we need to think back to our year 10 work here. So nanoparticles are really, really, really small. And because they're really, really small, they've got a greater surface area. So when we're talking about nanoparticles, we normally talk about surface area to volume ratio. But it's allowed you to just say surface area here, because when we talk about catalysts, we just talk about surface area. So it's 1 mark for saying that they have a greater surface area. And the reaction takes place on the surface of a catalyst. So therefore, there's going to be more frequent collisions, or the rate of reaction is going to be faster. Okay, so last exam question now. So yeast catalyzes the fermentation of glucose into ethanol. Name the type of catalyst that yeast is. So pause the video. Okay, so hopefully you've come up with the idea that it's enzyme, because we know that yeast is an organism and therefore it's biological. Okay, that's the end of the lesson. Thank you for listening. See you next time.